This is the fourth video of Chapter 18 of the Crystal Clear Electronics video curriculum. In the next few minutes, we are going to make an LED running light that we can control from our computer.
Let's get started. The schematic of the required circuit is shown in this figure. We connected the anodes of the LEDs to one pin each on the same port and the cathodes of the LEDs to a ground via a resistor. The LED is a nonlinear component that can only be driven by a current source. In this example, the resistor acts as a current source by limiting the current. The voltage drop on an LED is around 1.7 volts when open, meaning that current is flowing through it. At 1 milliampere, it is just barely lit, and at 10 milliampere, it lights with full brightness. The supply voltage is 5 volts, and the voltage drop is 1.7 volts, which means that 10 milliampere should cause a 3.3 volt voltage drop on the resistor. So, the resistance can be calculated by the well-known formula R equals U divided by I, which gives 330 ohms. If only one resistor is used for all the LEDs, only one LED can be lit at a time, because otherwise the brightness would decrease depending on the number of LEDs on. The more LEDs were lit at a time, the less current would flow through each LED.
The point of a scanner LED strip is to move an illuminating LED to the left or right with the appropriate command. If the commands are sent often enough in succession, then we get an LED running light.
An attentive viewer may have noticed that all LEDs are connected to port B. This is no coincidence. The reason for this is fairly simple. It is easier to write a program if you only need to control one port. There are many ways to start writing the source code. This time we will follow the so-called bottom-up approach. In the C language, the most important part is the data and the operations executed on it. To put it simply, data is the variable and the operation is the function. The bottom-up method involves thinking about what data you need and what operations you need to perform on it to achieve the desired functions. When all the components are ready, all you have to do is put them together. Let's see what data we need in this case. You will definitely need the port B register, which represents the state of the LEDs. If one of its bits is 1, the LED connected to the corresponding pin of the IC will light up. You will also need the UDR register, where you can write the UART data to be sent and read the incoming UART data.
It can be a bit confusing here that the same register is used to send and receive UART data. This is due to the characteristics of the UART peripheral of the ATmega16A microcontroller. When we write in the UDR register, the data is written to a specific register in the background. And when we read from the UDR register, we get the received data from another register. We don't need to deal with this when writing the program. We just wanted to resolve the apparent contradiction.
We won't need any other data, but we will need operations. First, we need to initialize the ports and the UART peripheral, so we need to write a function for each. We will need two more functions. One will move the running light to the left, the other to the right. Finally, we need a function for transmitting and receiving data on UART. During initialization, we need to set the I/O pins the LEDs are connected to as outputs, that is port B. And the UART has to be set up basically in the same way as in the previous video. The next operation is to shift to the left. If we want the LED on a given pin to be off, we need to write binary 0, and if we want the LED to be on, we need to write binary 1 in the port B register to the correct position. There is only one LED on at a time, so all possible combinations on port B are the following, represented in binary, hexadecimal, and decimal numeral systems. The task of the function is to shift the bit whose value is 1 in the number to the left. For this, in the C language we can use the binary left shift operator, i.e. double smaller marks. This operator shifts the integer to the left and it brings in zeros from the right. We can use this operator every time except when the state is 1, 0, 0, 0, 0, 0, 0, 0. This is the leftmost state when the cycle restarts, and the next value will be the initial value 0, 0, 0, 0, 0, 0, 0, 1. The accomplished task is the following. If it is not the final state, move the light to the left by 1. If it is the final state, port B should contain the initial value again. This can be expressed in the C language using the question mark colon operator. In the first bracket, we check whether the leftmost LED is off, which means that port B is not equal to 0x80. If our condition is true, the LED is not lit, we perform the operation in the brackets after the question mark, moving our 1 to the left. If the condition is not satisfied, in other words we are at 0x80, then the rightmost LED is lit, so port B should be 0x01. We can implement the same operation with the if-else operator. If port B is not equal to 0x80, we shift port B to the left, otherwise it should be 0x01. Shifting to the right is analogous to shifting to the left, except that here the right final state, that is 0x01, should be treated differently. If we haven't reached the rightmost state yet, we shift port B to the right, otherwise we turn on the leftmost LED.
Now we are done with our LED control functions. We still need to deal with the UART data.
Let's start with receiving the data, as we haven't done that so far in this chapter of the curriculum. Let the function name be uartReceive, and let it return a single received character. As mentioned before, we can read the received data from the UDR register. We can see when data was received from the state bit of 7 of the UCS RA register. The name of this bit is RXC from the abbreviation of the receive completed, which means that the reception has been completed. If RXC has a value of 1, then new data has been received and is available in the UDR register, so we wait for this condition in the while loop. If data has arrived, we read it and return it at the end of the function. We can simplify the source code if we know that AVR libc, that is the subset of the standard C library released by Atmel, contains a macro with which we can wait until a bit is set. This macro is the loop until a bit is set. Its first parameter is the register we want to wait for a bit of, and its second parameter is the bit's sequence number. In our case, these will be the UCS RA register and the RXC bit. Let's call this function by a different name, say uartGetChar, and let its parameter be of type file pointer. We'll see in a moment why it makes sense to do this way. It is also possible to use functions from the standard C Studio library in the microcontroller. Practically, the data sent and received will be redirected to the uart. To do this, we need to override the studio in and studio out variables, which are defined in the studio library, well hidden from us, so to speak. To override them, we need to create a variable of type file, which links the studio functions to uart. For this, we can use the fdev setup stream macro. First, let's prepare the data reception. The first parameter of the macro is a null pointer. The second parameter is a function that returns with a received character. Well, that's what we just created, called uartGetChar. The last parameter of the macro should be the substring fdevSetupRead, since we are reading from uart. When the macro is called, a buffer of type file is created and saved in a variable called uartInput. All we have to do is redirect stdin to our newly created buffer, making stdin equal to the pointer of the uartInput variable. From now on, we can use the getChar function to read a character from the uart. You should also do the stdio redirection to send the data, so you can use the printf or puts functions. To do this, we need to write a function that sends a single character. Let's call it uartPutChar. In the previous video, we showed that we can send data by writing to the UDR register, but only if the UDRE bit of the UCS RA register indicates that the UART peripheral is ready to send. There's one more small snag that we need to fix. In standard C library functions such as puts, after the last character of the string is sent, a \n new line character is sent as well. The problem is that our computer is running Windows, and the new line is not a \n, but a \r and a \n character. So what we do in this function is that if the character to be sent is a \n, we send a backwards r before it.
The \r character is called carriage return. It is also referred to by CR. The \n character is called line feed. It is often referred to as LF. These characters actually date back to the days of typewriters, where you had to pull the print head back to the beginning of the line and then raise the line by moving the paper. The next thing we need to do is to create a temporary buffer here as well, which we can pass to stdout using the fdevSetupStream macro. In this case, the first parameter will be the uart_putchar function, the second parameter will be a null pointer, and the third parameter will be an _fdevSetupWrite since we want to write to the uart. Finally, the standard output is redirected to the uart by setting the standard out variable to the pointer which points to the uart output variable. There are two ways to send a series of characters. Without formatting, use puts, or with formatting, use printf. For example, let's say we want to send out a string that says hello world. This can be done as follows: puts hello world. If we want to print something more complicated, we need to use printf. Suppose a sensor is connected to the microcontroller that measures the temperature outside. This data is stored in a variable called temperature, and we want to send out this information using uart. The sending can be done with a single line of code as shown here. The percentage symbol $d means that the value of the temperature variable will appear in its place as an integer. And at the end, we insert a new line character. All we have to do is put the previous parts together in the main function into a working application.
The complete source code can be downloaded from the website. I will now try to highlight the most important parts of the main function. In the top 3 lines of the code snippet, we define 3 special characters to control the LED chaser. 0x55 is the character code for the capital letter U. When this is received on the UART, we negate the status LED. 0x3c is the character code for the smaller than sign, which moves the LED to the left. 0x3e is the character code for the larger than sign, which causes the chaser to move to the right. At the beginning of the main function, initialize the ports by calling the IOInit function. Then, we set port B so that the rightmost LED is lit. The UART peripheral is also initialized with a baud rate of 4800 by calling the UARTinit function with 103. Then, we redirect stdout and stdin to UART. The initialization is done, which is indicated to the user by sending the UART initialized text. In the infinite loop, we always wait for a character to arrive on UART. If the data arrives, we check to see if a command was received. We do this with the switch case operator. In each case, a unique text is sent on UART to the user to confirm that the command has been received. If a capital U is received, the status LED is negated by negating port A. If a smaller than sign is received, we move the running light to the left by calling the running light left function. If a larger than sign is received, we move the running light to the right using the running light right function. For all other characters, we just send a message on UART that we cannot interpret the command. Once we have the code, there is nothing left to do but ask Dávid to upload the code to the microcontroller.
Already uploading.
Wow, the LED flashes and this red LED lights up, so that means we're in the default state.
Yes, we now send the letter U with H term, which hopefully changes the status of the status LED.
remélhetőleg megváltoztatja a...
And you can see that it is not lit now.
Nem világít. Ha küldünk még egyszer,
If we send another view, it will light up, so the status LED is working.
most akkor következőnek
Now, we'll next look at what happens when we send a relational sign, first say the less than sign. We can see that now an adjacent LED lights up.
föl, küldünk ismét egy...
We send the same character again, and as a result, again, an adjacent LED lights up.
A következő LED villant föl,
Now, the LEDs will hopefully light up in the other direction.
remélhetőleg, és így van.
And it does, so when the greater than sign is sent, this is what happens. By sending it again, we are back to the default state.
Visszaértünk az alapállapotba.
I don't know how the right and left side will appear on the camera, but I do know that you can move the LED position in one direction with one sign and in the other direction with the other.
Itt a hátterm
In the H-term window, you have an option called AutoSend,
ami pedig azt csinálja nekünk, hogy
where you can set the number of times to send the given command
ezt a parancsot, és hogy milyen késleltetés.
and the delay between the repetition. In this case, let's set it to send this command 100 times with a delay of 0.
Küldj el 100-szor ezt a parancsot. Ha rányomunk, hogy start,
Press start and you will get a running light.
Not bad. I say we worked hard for the experience. Now you can use UART communication in any project. I hope you find these few tips useful.
ezzel el is érkeztünk a videósorozat.
This brings us to the end of the 18th chapter. You will find the written curriculum and all the necessary information and links below the video. Follow us on Facebook for the latest news and we'll see you soon in the next videos.
Sziasztok!
Bye!